with these two, we can actually write some programs. Not very extensive, maybe a little hard to handle things, but at least we get an idea of how the system works. So I'm going to write some code here, a program to find the sum, let's say 36 plus 13, and we want to leave the answer in register 0. Okay, now there are a couple of problems associated with this thing that we have to solve, and the first one is one that will be easier handled when we do another addressing mode, but just to kind of focus with these things, why we're going to do it here. Here's my strategy, and boy, you know, we always used to require people when writing programs to do a flow chart, a design, a layout. You know, this is what I'm going to do. When you start working in assembly language, it is significantly more important to do that. You need to have some kind of an idea as to how you're going to attack this problem, what you're going to do with it. So here's my strategy. The LC3 generally will begin execution with the registers all containing zeros. Not a good idea to count on that. Particularly because one of the common things with assembly language work is that you'll do a task, write the code for that task, which becomes part of a larger problem, and you just copy the code into that larger problem. And if you take this sum code and put it in something that has previously been working with those registers, it may not have zero in it. Okay, so I'm going to clear register 0. In other words, I want to make sure that there are zeros there. Then I'm going to get a 36 into register 0, and then I will add the 13, and that's the end of what I'm after. So I have kind of a strategy here as to how to do this. Okay, now, as you attack these things, we have to get to the point where we have some kind of a feeling for this instruction set so that we know how to accomplish certain tasks. If you read through the instruction set on the inside back cover, there is nothing about clearing a memory location. So you have to figure out kind of a sneaky way to do it. And the sneaky way is to use the AND instruction. If you do an AND between that register and the number 0, and remember, does a bitwise AND through the whole 16-bit word, and it puts a 1 in the answer if there's a 1 in both operands. So if one of the operands is all 0, the result's going to be all 0. Okay. So my first instruction is going to be AND with an immediate operand. If you look at the instruction set on the back cover, That's the fourth operand down, fourth instruction down. The opcode is 5.
So are you gonna be writing this program in binary then?
Absolutely.
Do you expect us
'Cause
to
we
write
don't-
our programs in binary?
Your first assignment, you're going to write in binary. Yep. Our destination register, well, it's register 0 that I'm going to try and work with. That's where I want things to end up. Source register. Well, the source is also register 0. I want to take register 0, what's in there, do an AND with the number 0 and put the result back into register 0. So my destination and source are the same. Not unusual. In fact, you're going to see it again here later on. Now, since I'm going to use an immediate operand, the next bit is 1. That says that it's an immediate. And the last 5 bits then are my operand. Well, it's 0. 0 operand. Okay, the net result of this instruction is that it will clear register 0. Okay, whatever was in there, if it had garbage like that in there, remember the way these immediate operands work, they take those 5 bits and then they copy this bit all the way over to the full 16 bits. And then it does an AND, bitwise, 0 and 0 is 0, 0, 1 and 0 is a 0, 1 and 0 is a 0, so on. We get all zeros. Where does it put that? It puts it into the destination. Okay? See how that works? Okay, we got that one. Yeah,
So the first 0101, that's the AND?
right.
Okay.
That's the opcode for an AND. Okay, so now we try the next step. I want to get a 36 in there. Trouble. Because the biggest positive number I can get in 5 bits is 15. Well, that's all right. I can still do it. This is AND. Opcode 1 is add. Okay, I'm going to add to register 0 and put the result in register 0. I'm going to add 15, that's what this is, to register 0, which I just cleared, and put the result in register 0. So register 0 now has 15. Oh, hey, I'll just do that again. has a 30. I'll do it again. But now, I had that right the first time. No, I didn't, because I've got to have 5 bits, not 4. 0, 0, 1, 1, 0, there we go. That's a 6, so register 0 now has a 36. Okay, point being that I can kind of phony bigger numbers than the 15 that I'm limited to in immediate mode. There are better ways. And we will get to better ways here before the hour is over. Okay, so now I've got the 36 in there. So now I'm down to this point. Now I've got to add the 13. Well, gee, that's just what I've been doing all along. I'm going to take what's in register 0, add this number, which is 13, and put the result into register 0. So register 0 now has 36 plus 13. That wasn't too bad. And then the halt instruction, which we use to end the programs. Let's see, it's a trap instruction, and, well, they don't have it right back there.
They have a trap at the very bottom.
It's what?
They do have a trap at the very bottom of the chart,
Yes.
but that's not what you're looking for.
No, there's another item that's needed as part of that.
Halt is on page 169. as an
Yeah,
example
it's
of-
trap 25. The idea of the trap instruction, let me just point this out. If you look at it, you have these 8 bits, and then it has what's called in here a trap vector. Here's the idea behind the trap instruction. It's actually a call to the operating system to perform a function for you. And there are a lot of different functions that the system can perform. Input and output are classic examples. You don't handle input and output generally directly from within the program, although we will do that before we're done. And you'll see why it's usually done as an operating system service, because it's a mess. But what we mean by a trap vector is that it gives an address for the beginning of the routine that this will handle. What a trap does more or less is a jump to a particular address. Changes the program counter so that it goes down in and finds these instructions and starts executing them. the vector that we work with here is 25, hexadecimal 25 is the halt routine. Now, my son is doing some work with the Intel processor, and that has a halt instruction, but the command is you don't ever use it. And this is very often true of halts in assembly languages, because what it does is it shuts down the whole system. It literally halts the processor. Now, in this case, it will not. It will stop the LC3 system, but your computer will still be running. Okay, so it's a little bit different kind of situation. You'll still have the window up there that shows you the contents of all the registers and of memory and your program and all the rest of that. Question?
What's that second block of bits there on the trap?
This one?
Yeah.
They're just always zeros for a trap vector, trap instruction.
And the 4 ones are indicated.
The 4
as a
ones
trap.
is the trap opcode. Okay, we have, this is the AND, add, and those are the 3 that we've talked about. We'll talk about more.
So when you shut down your OS, the very last command that goes through the processor is that halt? When it shuts down?
When you turn your computer off?
Yes.
Yeah, that's the last instruction. It just literally halts the processor. The program counter does not have a legitimate address to go to execute another instruction. It just stops. Period. So this is a pseudo halt. It halts the LC3 system, but will not shut down your computer. Okay. That's a program for this LC3 system. It doesn't do much, but that's all right. You can see where we're working in here. These are all register modes. And everything else that I did in here, except the trap instruction, these are all immediate mode operands. Okay. Any questions there? Okay, let's get one more addressing mode, and then we'll try and write another instruction. Well, we may end up writing the same one. A really common addressing mode is PC relative. That is that we reference a memory location by using the program counter where we are. Let's see. The classic instruction for that we will work with here we get another opcode up here. It's LD, which stands for load. And it's used to transfer contents of a memory location into a register. The load opcode is 20010. Then you have a register it's a destination. It's the register where you want to put this value. Then the remaining 9 bits are an offset to the program counter. And here's the way it works. It will take those 9 bits, does a sign extension, that is, the most significant bit here of these things is copied until you have a 16-bit number. Then you add that to the program counter and fetch from that memory location. So for example, as you do this thing, you have to understand how that program counter works, and the value that goes into that offset will change if the location of this thing in memory changes, or the location of where your value is that you're looking for changes, unless they change in lockstep. If they're always the same distance apart, it won't matter. You'll see how that works here. Let's suppose that we're at location 300 and we're going to load something from down here at 325. Here's our data, whatever it is. These are hex numbers. We always work in hex. So what's my instruction going to look at like? Well, since we work with register 0, we'll work with register 1 this time. Now, I'm going to have an offset over here. That's going to be added to the program counter. As I'm executing this thing, what's in the program counter? 301. Rule. Keep this firmly in mind. When an instruction is being executed, the program counter contains the address of the next location in memory. So you see, I want to put a number in here where I have, let's see, if we're looking at 16 bits. 0325. I want to add something onto that 301 to get 325. Well, that's not hard. It might be if we had particularly grubby numbers, but in this case it's not. So I need a 9-bit number here that has this value. Well, 4 looks like that. 2, and then the 9th bit. Now obviously there's a limit to how far you can go with this. You can't get anywhere in memory because there's a maximum distance here.
But in that case, you could just run the command again, right, to get further out.
There are other ways to handle it. We'll just say that for now and talk about it later on. But PC relative, there is a limit. You can go forward, you can go backward. That 9-bit, if that leftmost bit's a 1, it's a negative number, you'll be referencing memory locations before where you are right now. Okay. But this instruction will reach down into memory a certain distance beyond where we are and fetch a value out of that memory location. Now, here's a kind of a strategy layout for programs written in this assembly language. We do this, we tend to do our code ending with our trap instruction, and then we put our data down here. You don't have to, you can do the data first. This is von Neumann architecture. One of the assignments you were working on said to describe the von Neumann architecture. One of the keys to that was that you can mix data and instructions. You just have to be sure that you don't try and execute your data. Because who knows what those data values are going to mean as instructions. That's why you have to have this trap in here to keep from, because as long as that program counter, as long as it doesn't get anything else set to it, it just keeps going to the next memory location and keeps executing the instructions. It'll go right down into the data and execute them. So, let's see what we might do here with this program that we had up here earlier where we wanted to add 36 and 16, now using this kind of an approach, using PC relative addressing. Well, I want to get the sum into register 0. That was one of my things. So I'm going to begin with a load instruction. So, and we'll load into register 0. And for right now, I'm just going to leave that offset blank. Very often do this in working with things at this level because you don't know yet exactly where you're going to put that data. But as soon as you find out, then you can come back and fill the thing in and accomplish it. Now, another point, using the load, we don't actually have to clear that register. Remember, as I was talking about mailboxes, and the problem with the mailbox analogy is that you can put lots of letters in a mailbox. You can't put lots of values in a register. As soon as I load that register with something out of memory, whatever was in there before is gone. Just, boom, it evaporates. So I don't really need to go through this process. I don't really have to clear it. I can get that 36 in there in one instruction. Add, oh. I'm going to add on to register 0 and put the result in register 0. 13 is nice. I can do that as an immediate operand. Okay, so I'll just put that magic 1 in there that says that this add is going to be an immediate operand. And then I've got my 5-bit operand for my 13. Then I'll hold. Okay, now I can put my 36 down here. Let's see, 36 is a 2-4 in hex, so in hex I've got a 4 and a 2. There's my data. Now, where is this thing in memory? Well, we don't really know. Let's just suppose that we're beginning in location 100. Then this would be in location 101, this is 102, and this is 103. Now I can figure the offset that I need. Remember, when this instruction is executing, the PC has a 101 in it. So 101 plus my offset, whatever it is, has to be the address of my data. 103. Oh, cool, my offset is 2. Now I can go back and fill it in. There we go. Now, just notice this, that if that program is loaded someplace else in memory, let's suppose that it's located at 248. This would then be 249, 24A, 24B. If I come to the address of the next instruction, 249, add my offset, 9 and 2 is 11, that's a B. 24B, sure enough, that's still the address of my data. That's the real advantage of PC relative addressing. There's another mode that we call absolute mode, where you would give the actual address, the physical address of that data. Well, if it gets moved to someplace else in memory, it has to be changed. This one doesn't. No matter where it's loaded, it'll still come out.
Is that PC offset always going to increment by 1?
It always begins from the address of the next instruction.
Okay.
Because, again, as an instruction is being executed, the PC always contains the address of the next instruction. And so as it decodes that offset, that's what it's going to add it on to. Yeah?
So it increments it to the 103 to where the data is, and then you just go to the next one?
Oh, it does not actually change the PC, by the way. If, let's see here. But yeah, that's not a good idea. Oh, here we go. There's a diagram on page 126 of the book that gives a pretty clear idea of what's actually going on. I'm going to skip part of it here, but you've got your instruction register where the instruction is being held, and you've got your offset here. Now we've also got the program counter down here. We take an adder, the program counter goes into 1, this thing goes through a sine extension, and that goes into the other one. The output of this adder goes into the memory address register. It does not go back into the PC. Okay, so the PC itself is not changed. It's used, but it's not changed. Okay?
So you come up through one more time, so it's doing the offset and the sine extension.
Yeah, it takes this offset and basically converts it to a 16-bit number so that it can add it by duplicating this bit. That's the sign extension. That's added on to what's in the PC, and the result is put into the memory address register, not into the PC. So the program counter will still contain the address of this instruction, so that when you're through with this and it goes to fetch the next instruction, it's still looking at this value. Okay, yeah.
The opcode 000, what is that? We talked about that one.
Oh, that was my mistake. Oh, this is not an opcode.
Data.
This is data. Now, that's one of the problems, see. If the thing did not trap and went on down and tried to execute this instruction, what would it come up with?
Try to branch.
Yeah, that would be interpreted as a branch instruction, and it would try to go to this address, which means what? Well, it doesn't mean anything, because it's data that I was trying to work with. So, again, that's part of the point of von Neumann architecture, is that you really have to control what's going on with each memory location as you go through, so that you make sure you don't try to execute your data. That's why I really need this trap or halt instruction at the end of the program. Otherwise, it will try to execute this and goes off into who knows where, and you get all kinds of bizarre stuff happening that you don't have any control over. Because it's just looking at whatever's in memory, wherever it is. Yeah?
So does that mean you can only put the data at the very end?
No. Some programmers like to put it at the first. Then there's a trick that you have to pull to make sure that it doesn't start executing where the data is. You have to give it a different, what's called transfer address, where it will begin execution. Make sure that it begins after your data. And then your relative offset would be back to an earlier memory location. Let's just see how you might do that. For the sake of discussion here, let's just say that we've got some data. And then we begin our program with a load instruction, which is 101, and we'll load register 3.
Yeah, is it load 0010?
Oh, yeah. 101 is and, isn't it? And 0010. We'll load register 3, and then I'll figure an offset here in a moment. Again, let's suppose that our data there is at 36A, this would be 36B, and this would be at 36C. Without being concerned about what that next instruction is, we can figure our offset here. Remember, it takes the address of the next instruction, because that's what's in the PC, and is going to add an offset, plus an offset, has to equal the address of my data. Okay, this is the next instruction, and this is my data that I'm trying to get to. It's not the actual data, that's the data location. Well, that says that my offset is 36A minus 36C. Which is -2. Oh, 2's complement. Okay, we've got a 9-bit offset. There's my number. The usual scheme for getting that is you toggle all the bits and add 1. So there's my offset. Does it work? Well, it's going to take this thing, that's an FE, those last 8 bits. It takes the leftmost bit, the sign bit, and duplicates it all the rest of the way across. So now it's going to have FFFE. That's going to be added to my program counter. So I've got 036C. And I'm going to add this. Now you can go down and do it in binary. With a little practice, you can do it in hex relatively easily. You just have to think about how you represent numbers and what these things are. C is a 12, E is a 14. 12 and 14 is 26. Oh, that's 1 times 16 plus 10. 15 plus 1 is 16. Okay, there's 16, and then the 6 that you carried. 15 plus 1 is 16. 16. And that's what goes into the memory address register. And sure enough, that's where my data is. So I can look backwards as well as forward. Again, the biggest thing you have to control in all of this is to make sure that you don't execute your data as an instruction. If you've got data intermingled, you got to either end before you get to it, start after your data, or somehow branch over the data if you've got it in the middle somewhere, which you can do. Generally considered poor programming practice, but you can do it.
So we have an assignment?
Do we have time?
Some of us have to run.
Yeah, you better just go. I'll give you one on Friday. Don't have time to